What are Fischer projections, and how do we use them to determine the relationship between stereoisomers? Let's find out. When we're looking at molecules, usually we're looking at bondline structures and the viewpoint is from the side. A Fischer projection, on the other hand, has us looking at them from the top down instead. So, for example, in this molecule, if we number the carbon chain so we can keep track of our carbons, and if we look at carbon 3 from the top left, then chlorine and bromine would point up towards us and the carbon chain would be pointing down away from us. We can redraw the molecule from this perspective using our wedge and dash notation, where the carbon we're looking at, carbon 3, will be the dot in the middle that they're all bonded to. The Fischer projection is this view, but drawn as a stick figure. No dashes or wedges. They're implied. Vertical lines will always be dashes away from us, and horizontal lines will always be wedges towards us. So a Fischer projection is a flattened out, top-down view of the molecule. Fischer projections are often used in sugars to highlight chiral centers and to help us assign configurations to those chiral centers. These configurations can be assigned using the Kahn-Ingold prelog priority system. Let's consider this Fischer projection with two chiral carbons. On the carbon in our first cross on top, hydrogen is priority 4 and oxygen is priority 1. Our remaining atoms are both carbons, so we have a tie for priorities 2 and 3. Looking at what they're attached to, the top carbon is attached to 3 oxygens and the bottom carbon is attached to an oxygen, carbon, and a hydrogen. Oxygen to oxygen ties, but then oxygen beats carbon, so the top carbon gets priority 2 and the bottom gets priority 3. If we look at how our priorities are arranged, 1, 2, 3 is counterclockwise to the left, so it would be an S configuration. However, CIP assumes our lowest priority, our hydrogen, is on a dash, but here, the hydrogen is on a horizontal line, which in a Fischer projection means it's on a wedge. But that's okay. We don't need to do any additional work. We can just reverse the configurations. It's an R configuration. Now we can do the same thing to the next chiral center. Again, oxygen is priority 1 and hydrogen is priority 4, and again we have a tie with the remaining carbons. Oxygen beats hydrogen, so the top carbon is priority 2 and the bottom is priority 3. Our priority twists clockwise to the right and the configuration would normally be R, but again, because hydrogen is on the horizontal line, it's on a wedge, so we reverse it and the configuration is S. And this is almost always going to be the case in a Fischer projection, that we need to reverse our configurations. What else can we do with Fischer projections? Fischer projections are useful for determining the relationship of stereoisomers. If they're mirror images, they're enantiomers. If they're not, they're diastereomers. For example, to get the enantiomer of this molecule, we set up an imaginary mirror. The top and bottom remain the same, then we draw what's closest to the mirror, and farthest from the mirror, farthest from the mirror. In other words, everything on the right ends up on the left, and everything on the left ends up on the right. If we want to confirm this is the enantiomer, we can work out the new configurations. The only priorities that have moved are on the horizontal lines, so connected to the first cross, the top carbon is still 2 and the bottom is still 3, but now left is priority 1 and right is priority 4. And same thing on the bottom. We now have 1 on the right and 4 on the left, and it flips the configuration. Since all our configurations have flipped, we indeed have an enantiomer. If we're comparing two molecules and only one of the chiral centers is flipped instead of all of them, that would make it a diastereomer. Let's say we're given a molecule and we want to turn it into a Fischer projection. We would start by taking all the carbons pointing down at the bottom of our bondline structure and flipping them up, bending our carbon chain into an arc. The carbons that were already pointing up don't need to be changed, but on all the carbons we flipped up, we also flip their dashes to wedges and their wedges to dashes. Then, to help us keep track, we can label the left carbon as the top and the rightmost carbon as the bottom. Now we have a spiky caterpillar inching along. If we imagine looking at this molecular caterpillar from above, we can draw out our 6-carbon chain in a Fischer projection, with 1 for the top carbon, 1 for the bottom carbon, and 4 crosses in between for the carbons in between. The leftmost group at the top is a CH3, and so is the rightmost group at the bottom. To fill out the middle, remember, wedges come towards us and dashes away from us. That means the wedges are pointing to the caterpillar's left, and the dashes to its right. Or from above, that the chlorine is on the bottom side, its left, and the bromine is on the top side, its right. The rest of the spaces we fill in with the unwritten hydrogens. Then we can rotate it so the head is up top and the caterpillar's bottom is at the bottom. There's our Fischer projection. Summing that all up, we 1. Flipped all our carbons up, 2. Marked the leftmost carbon as the top and the rightmost carbon as the bottom, and 3. Put all the wedges on the left and all the dashes on the right of our Fischer projection. What about going the other way? What do we do if we're given a Fischer projection and need to convert it to a bondline structure? We use the same steps we use to make a Fischer projection, but flip the carbon chain last. To start, we draw our carbon chain the same length as our projection, and to help orient ourselves, label the leftmost carbon as the top and the rightmost carbon as the bottom. Then, from left to right on our bondline structure, we add everything from the Fischer projection starting at the top. Everything on the right is a dash, and everything on the left is a wedge. Once everything's on the bondline structure, we flip down every other carbon, changing any wedges to dashes and dashes to wedges when we do. And there's our bondline structure. Once we start to get really comfortable with these conversions, we can do them all in one step. We can mark our first carbon on the crosses on our Fischer projection up, and we know the group on the right is going to be a dash. Then we also know we're going to flip our next carbon down, so the dash will become a wedge. Then we repeat up dash, down wedge, etc. all along the chain. Anything on the left will be the opposite of whatever we determined was on the right. Then we just transfer them over to our bondline structure.